Good morning, everybody. Good morning, Rob. This is the next lesson that we're going to have. It's based on the first lift over the project at 1860 South Ocean. I want you, when you watch the video, to take some special attention to things we've talked about in the past. We've talked about XY axis. We've talked about benchmarks. We've talked about planning ahead. Take a look at these things, watch the video. We'll have a little talk afterwards, okay? Okay.
Hi, I'm Devon with RWB Construction Management. In our last video, we learned about pile caps, grade beams, and the slab pour. In this video, we'll be learning about cast-in-place walls, block walls, tie beams, and the interior layout. All right, let's go down to the slab and take a closer look at what we got going on. When we talk about interior layout at this stage of the build, they're just doing a preliminary layout, snapping lines of all the walls, chase walls, interior walls, everything for the first floor, making sure that everything is where it's supposed to be. Over here, we have one of the first steps that happens after the slab is poured. This is an XY access line, and you'll see these all over the slab. From the north side to the south side, and these are put here by the shell contractor. We actually like to have the framers come in, the interior framers, and double check and make sure that their lines line up with these lines so everybody's on the same page and working off the same plan when they come down to the slab. When we have the interior framers come in to verify our XY access lines, we also have them lay out the entire floor on the ground with chalk lines and make sure that all of our slab penetrations line up with where they're supposed to be, and that we don't need to move something or something got bumped during the pour and is not where it should be. So over here we have a good example of that. In the wall that is between the laundry room and the storage in the garage. This storage room also has several mechanical units, AC units, and they come up inside the wall. So at this point they're kind of faded, but they've actually snapped out the line for the wall, and these all line up and fit in that wall perfectly. Once we have our XY access lines, now we can actually start putting up our form boards and everything, because we can measure from those lines to get the correct placement for our walls. So now we have the back side of our forms, and then they start installing the rebar. Same thing as grade beams, all the rebar is specified by the structural engineer, size, distance between them, and everything. So we make sure that this gets inspected before we close it up. So that's an integral part of our process, is making sure that we schedule those inspections early enough to where it's not holding up our process of putting this side of the form boards up. In this stretch, we have a bathroom, a laundry room, a staircase, and a storage room, and then it goes on to the garage. This wall is a cast-in-place wall. These are the forms for a cast-in-place wall, and we'll show you the finished product in a minute. This is the form for a column, and once that cures enough, it'll be stripped. Over here we have a block wall that has filled cells. So block have two voids, one on this side, one on this side, and they're staggered. So in this wall, the engineer has called for them to be filled cells. That means we put rebar down into the cell, and then we come back and fill it with the concrete. These are weep holes, and those are knockouts. So everywhere there's a knockout, there'll be a weep hole above it. And the knockout serves two purposes. One is for inspections, so that the inspector can come and look that there is rebar going from the bottom all the way to the top up into the tie beam. It also serves as a window. When we pull the form off, we can make sure that this got filled all the way down to the bottom. Same thing with the weep hole. The weep hole allows us to see when they're pouring that concrete did in fact make it all the way down to this point and then down to the bottom. Now over here, we have a column that's been poured and this one's been stripped. So you can see these little pieces of bar that help hold the forms in. They will come back with a grinder, cut them flush, and then spray paint them with a rust-proof paint so that it doesn't bleed through. Once we come over here, this is in the garage. These are the finished product of the cast-in-place walls. This has been stripped from the forms, and then they have similar pieces of metal sticking out, and the same process will happen with these. They'll get cut flush and then spray painted over with a rust-proof paint. So if you look up here, we have the tie beams. Now, tie beams tie all the walls together and get poured all in one shot. The metal plates that you see up there are plates for the joists. They get welded to those plates. And the back of the plate, I don't know if you can see them, but they have Nelson studs that get poured into the beam, and that's what holds them into the concrete. Over here I have an example of the plates. These are Nelson studs, and typically it would go in something like this and gets poured in. Then once the concrete dries, we can weld to it, and that's how the joists get put in. We're inside the house looking into the theater. This is a very good example of how a tie beam and the columns all get tied together. You can see how the beam comes across and over and down. All that will get poured in one solid pour. You can see the different size hoops, the different size bars. You can see how on the column, how all the bars turn. All that gets specified by the engineer as well. Just an easy example of how it ties all the walls together and keeps everything tight. When you're pouring the slab, one of the things that can happen is a pipe gets shifted because of the concrete pump pushing a lot of concrete around, or a conduit shift. And so we actually have the interior framers come in and lay out all the walls on the slab just as a preliminary layout. And that tells us where all of our pipes are and make sure that they're exactly where they're supposed to be. This is a good example. This is the mechanical room, storage room, and fish tank equipment room that's just off the garage. This is the wall between that room and the laundry room. And as you can see here, all these pipes are exactly inside the wall as they're supposed to be. Over here we have a pretty important room. This is the AV room, and all these pipes need to land in the walls that they're supposed to. So this one we checked, triple checked, and made sure that everything was gonna land exactly where it's supposed to be. Right now I'm standing in the salon/spa area. If you walk over here with me, you can see this cutout in the floor was actually framed this way and planned because this is where a drop-in hot tub is going to be, and then we'll also have a cold plunge here, and all the plumbing will be underneath those items.
Thanks, sir. All right. So we talked about a few things. One of the things that Devon stressed was the XY axis. This is probably the beginning and the most important thing you're going to do. The XY axis allows you to lay out all your walls square. It allows you to line up items on one floor to the next one. So elevators, stairways, things like that line up, okay? It also makes sure that everything in being square is going to allow your flooring to go in right. It's going to allow your ceilings to go in right. If you're putting down, as an example, a 24 by 24 tile, and your XY axis is not square with your windows, when you get to the doors, when you get to the walls, instead of your tile being nice and straight, it's going to be like this, okay? Because you have to be parallel. Everything has to be parallel. When they lay out walls, they can take them off of that line. Everybody uses the same line. You also saw on that video, there was a benchmark put up across. That benchmark is taken, we go to the highest point in the floor, unless it's some special item where it just jumps up, at which point we have to grind it. We set that mark up. That mark gives us the height. The doors are set, the windows are set. And in knowing the height the doors and windows are set, it lets you set the height of your tie beams. Because that tie beam has to be a set dimension in order for your doors and windows to fit. And you carry that through. We talked about before, that's the same dimension used to set outlets when they're a certain height, or switches when they're a certain height. All that has to happen. Now, when you guys were in school, you learned, and you're going to hate me for this, you remember the Pythagorean theorem? Yes. Very good. Okay. Pythagorean theorem says x squared plus b squared equals c squared. What that basically means is if I want to lay out a square to get my XY axis, I can go 3 feet by 4 feet, and when I go across diagonally, it's 5 feet. Okay? That way you know it's square. If that diagonal is more than 5 feet, you're not square. You're like that. Okay? So you want to make sure you lay it out. Don't lay out 3 foot, 4 foot, 5 foot. Lay out 30 feet, 30 feet, 40 feet, 50 feet. The bigger you make that triangle, the more accurate you're going to be, okay? Think of it as using a framing square versus using a small little something, okay? The XY axis is really important. So let's just go through a couple of things. You guys know what grade beams are. We covered them in the last video. Now you see tie beams. The one thing you haven't seen is a bond beam, okay? You've seen it here. This block forms a bond beam, okay? If you're doing a site wall, if you're doing a wall, for example, in this case, that goes around the generator room, okay? And the wall doesn't extend all the way up. You put a bond beam in, okay? You frame this up, and what's gonna happen, I don't know if you guys can see, you're gonna have rebar going through the top. That's going to form a beam when you pour it, okay? You're also gonna have bar coming up that ties into that. If you have a wall, say it comes up 5 feet, bond. If you have a wall that comes up 5 feet, for example, you've seen where air conditioning units are and things like that. If you come up and there's nothing locking this in place, right, it has a tendency to weaken it. Rather than pouring a full beam on top, like a tie beam would be, you form a bond beam. There's no lateral strength, lateral force on this other than whatever people put on them personally. But you need to lock all this in. You need to have the bar coming up, locking into horizontal. We call it horizontal framing versus vertical framing. They have to lock together. Similarly, this is called a Durawall, okay? This is a grid that goes between block on every second or third run, depending on how the engineer specs it. This is horizontal bracing. Okay, it does a couple of things. One, when the concrete shrinks, which it does, it gives it some strength. It also ties beyond the wall. So when you build a wall, you stick it out, and then when you pour the column, it locks them together. okay? What we have to realize in everything we do is we have vertical framing, rebar coming up from the slab, and we have horizontal. The connection of those two is what gives the wall strength. So when you do a bond beam and you pour across the top, you put the rebar in just like if you're doing a tie beam. The rebar coming up, the rebar tarring to the horizontal gives you the strength. Okay, so those are just some of the things you've seen here. You want to play the first. So there's a bond beam. Okay, top of the wall uses that block. Now, when they order block, there's 6-inch, 12-inch, 3-inch, 4. There's a whole bunch of different types. The shell contractor will know which block to use. Sometimes it's a matter of dimension. Sometimes it's a matter of function. In this case, it's a matter of function. This rebar will go around, and when it's formed, that will form a bond. Everybody got that? You go to the next one. Okay. You've got 4 kinds of forms. Okay, the earth form we carried in our first plans. When you dig out, we use it for grade beams, right? Now you've got 3 others. You've got wood forms, you've got metal forms, and you've got sonotube, which some people don't call a form, but it is. Okay? A wood form is made just by building a plywood box. Okay? But concrete weighs 100 pounds a square foot. So by the time you fill up this sonotube that's only 4 feet long, okay, that's 314 pounds of concrete. Okay? When I fill that up, you're talking thousands of pounds of concrete. So you have to lock it together so that it doesn't blow out. We call it a blowout, where all of a sudden the bottom separates and all the concrete comes spewing. The way that's done is with these ties. Now, the 2-bys are put there to give it strength because the plywood by itself wouldn't. Okay? So there's a couple of different types of ties we use. Okay? This is a drill tie. Okay? Simple piece of metal. You put a drill on this, and this side has a cutter. After they put the plywood up, they put it on a drill, and they drill it through the form. Now, why do they do that? Because if you had to drill a hole on this side and drill a hole on this side and try to fish this through, you'd be there all day. Okay? Doesn't make sense. So this comes, I don't know if you can see it, a little drill bit at the end. Okay? These are made for different sizes, for different thicknesses of walls. It's all planning ahead. So they drill through, and then they put a shoe on the end. Looks like this. Okay? The whole idea here is you're building the form, you're bracing it, okay, and you're tapping it off, okay? Now, when Devon showed you that video, he showed you bracing coming out of the wall, little pins sticking out of the wall that he said are going to get cut and sprayed with galvanized paint. That's this, okay? When it's done, you can see the little bends right here. They bend and they break, but they stick out from the wall because they're going to come out to here. So they cut them, they grind them, they galvanize paint over them. Galvanize paint so it doesn't rust through the wall. If you put waterproofing on, it doesn't matter. Okay? Go to the next one. Okay. The embeds he showed you in that video looks like this. Okay? There's many different purposes for an embed. Okay? In this case, the I-beams are going to be welded to each of these. Okay, these dimensions are taken, they're sent to the engineer to get approved, they're field verified, and they're done. These embeds are set and specified by the engineer on the drawing. We had the engineer come out. We had some questions about some of these because we needed to know if there was a differentiation between some and some others. Always check, okay? It doesn't matter. Go ahead. Oh. Okay, go back one. Leave it there, that's fine, leave it there. Okay. This is a stair we did on another project, and I put this picture in for a reason. You see this metal strip going up the wall? That's a 16-foot embed. Okay? It was 16-foot long plate 2 feet wide with Nelson studs all the way. This had to go in when the concrete wall was poured. But on this job, this wasn't specified to be a concrete wall. This was specified to be a cinder block wall. Okay? So if that's a cinder block wall, how do you put embeds in? So as you go through this, you'll find things. Doesn't mean somebody didn't make a mistake somewhere. Okay? So this wall was changed from a cinder block wall to a poured concrete wall because it had to support that embed. If it wasn't for the stair, it wouldn't have mattered. So I'll go to the next one. Okay, so in the end, these stair treads were all welded right to that embed in the wall. You have to think of this stuff ahead, because if you pour the wall and don't put the embed in, how do you put the stair in? You could always bolt it, but then you have a bolt. It's not going to be as strong as that embed. And the engineer will specify how it goes in. Either it's bolted or it's an embed, whatever it is. Okay, go to the next one. No. Okay, these are the ties we were talking about. Okay, that beam you saw, once it's stripped, it looks like this in these ties. These all get cut. They get sprayed with galvanized paint to stop it from bleeding through. They'll waterproof some of these. When they go over them later, you don't want them to rust, and you don't want the rust to come through the stucco. They got to be cut, they got to be ground, and they got to be galvanized paint. Okay, go to the next one. Okay, we talked about different kinds of forms. A sonotube is one kind of form. You saw the wood form. I don't know if you guys can see, this is a metal form. Okay, it's held together with pins and clips. It's a whole system. Okay, it works a little bit differently than the wood forms. Okay. You drill wood forms, you have drill ties. On these, you have different. You have an S tie, which is this, which will go through the pre-made slots in the form, and a key will tack into it, okay? In here, like that, okay? Now, when this is stripped, you'll see little pieces of S sticking out. Those get ground, just like this does, okay? There's advantages to using a metal form, okay? It's dead straight, it's quick, it's reusable. If I'm building a wood form that's only made to fit that dimension, it's very hard to use it again. But a metal form, I can repeat, and I can keep using it. Comes with corners, comes with straights, comes different heights. These are the short ones, okay? The only thing you got to be careful of is when you waterproof after using these, the concrete is very slick. We've had waterproofing companies come back and recommend different waterproofing methods depending on the type of form you use. Okay? Go to the next one. Okay, again, the same idea. Why is there two different types of bracing here? Because the amount of concrete that's going in there is excessive. Okay? You think of what I said, 100 pounds a square foot. This is like 4 foot square by 12 feet high. There's thousands of pounds of concrete in there. So this has to be braced off very well because it could very easily pop if it's not. Okay, go to the next one. These are the S ties, okay? So if you look at that, you look at this, you'll understand. This sticking out of the wall is after the form is removed. Then you cut them off, you grind them, and you galvanize them, okay? Next. Okay? This is the same thing Devon will show you. This is how it goes in before time. When they form, they're going to form over it because they want it in the wall, right? I go to the next. Okay, this is important, okay? This is called the turnbuckle, okay? You have to put bracing in to keep the wall straight, okay? The tendency is for everything to shift its own and seek its level. You want that wall to be dead straight, dead plumb, okay? If you don't put these in or some type of bracing, there's nothing to stop your wall from going like this. There's also nothing to stop it from going like that. These are really important to have an adjustment on them where if you're close, you can crank them one way, move it in, move it out. Bracing these walls is really important because it's easy to fix now. If you don't brace them or you don't brace them properly, they have the ability to move. And once the concrete forms and cures, your wall is where it is, okay? Take the extra step, make sure these are level. This is braced back, this is braced over, okay? Go to the next. Again, diagonal bracing to hold it up so it stays straight. This is not to keep the form together. This is to keep the form straight. Okay, go to the next. Okay, this is a bolt pattern in the floor. The engineer will usually require one of three ways. Either when a plate is put down, either it's put down with Nelson studs, like we said, you put this in the ground, they put the column on it and they weld it. Engineers don't always like field welds. They want them welded under controlled conditions where everything's perfect. So in this case, he wanted threaded bolts in the floor. There's also two ways of doing that. Many of you have seen J-bolts, where the threaded rod comes down and just turns. In this case, the engineer wanted these bolts to go down 12 inches into the pile cap. So this pattern is given to you as one of the bases for the columns, okay? You cut a piece of plywood, you put the bolts through based on the pattern that he gives you, and you use the plywood to hold it in place while you do your form. Okay, go to the next one. Okay, this is a column, and the reason this is like a combination, you see the Nelson studs? That's going to go up and grab into the tie beam across the top. The bolt pattern is going to go into that block I just showed you at the bottom. So you put that in. Now, this never sits all the way down. There's a bolt that goes under it, there's a bolt that goes over it. You can bring it up, you can bring it down, and then you pack under it with non-shrink grout. Non-shrink grout is used because concrete will shrink, it will crack, it will dry out. Non-shrink grout is going to hold you tight. Okay? So this would go up. We'll show you more of that in the next class. Okay? That's it. Okay. So we've gone through all this stuff. Okay? There are areas where we have block that's filled, like Devon was saying, and there's areas that the cells don't get filled. These are cavity caps. Okay? When a block doesn't get filled, cavity caps put on. That way, when they pour concrete, they know not this one, not this one, this one. Okay? Are they necessary all the time? No, but when a guy's got 12 trucks coming and he's trying to run through it and he doesn't want to look at a plan every 2 minutes, these help. Okay? It's cheap, they go in, they mortar them in, they do whatever, it doesn't matter. But it makes sure you have some kind of plan and order. Okay, so basically this is everything that we've seen that got you to that. Okay? Things happen here. You saw the area where the stair was. Okay? You saw that it was supposed to be block and it was this. You saw that sometimes these houses are built and they're the only one ever built. None of these are repeat like we used the same plan. And even if we did use the same plan, things change every time. One of the things Devon was showing you was a door that the owner decided, hey, I want to put that in later. So we went back to the engineer, we got plans, we did it. You guys are professionals, okay? You try to catch these things ahead of time. You're not going to catch everything, okay? What makes you a professional is not catching everything. What makes you a professional is how you deal with the things that come up. The issues that come up, do you throw it away and say, somebody fix it, or do you drive and take it? We're RWB. We go at everything, okay? Just assume that things are going to come up. The engineer is not going to talk to the architect. This week we had an issue where the designer changed something, didn't cloud it, it didn't go to the engineer. It's going to happen. You're not going to catch everything. Knowing how this works will let you come up with the right conclusion of how to fix things that do come up. The reason I bring all this in is not for show and tell, okay? The reason I bring this in is so you guys understand how this all goes together. So then when they come to you and say there should be a door here, You know, okay, I've got rebar there, I've got a column here. If I have a filled cell, I can cut this to here. You work with the engineer. If you don't understand how all this goes together, then you can't be part of that conversation. So it's important that as this stuff is going on in the site, that you guys follow, you look. If you have a question, you ask, why are we doing that? Okay? You're not going to pick this stuff up by osmosis. But you're all in a really good position because most people don't get to build something this massive. And every lesson you do. Justin, how much have you learned on sites?
A lot.
Okay? Drew, since you've been here. Okay? Guys have been doing this for years. They still come to these sites. They still learn because everything's new. Okay? Most of the times people learn because they're watching what's happening or they're watching what someone did wrong. And they'll know they'll never make that mistake because they saw it done wrong. Okay? Watch everything you learn. Be professional. Okay? Like I said, it's not catching everything. Being professional is dealing with the things you catch. And that's what we do. All right? Any questions? Sir.
Besides the Nelson stud, what reasons would the engineer pick a cast-in-place wall over a block wall?
Okay. Cast-in-place wall is going to hold a lot more weight than a block wall. Okay. When you do a steel column, you have a very small point load. We had talked in the past about if you go to the beach and put your finger down like this. Okay. He's going to determine what's the right amount of weight that needs to be carried and how to do that. Here, for example, in the garage, we had a 6x6 steel beam, a steel column that was designed. The architect walked through, engineer walked through and he goes, you know what? That's not enough. I know I drew 6x6, but that's not enough. So you can either add a second column there or you can make it a concrete column. Okay? Tell me which one you want and we'll do it. Okay? These things change. The architect, the engineer, engineers are notorious for coming out and said, I know that's what I drew, but. Or there are other jobs where we called them up and said, look, I know, like a 980, that big hangover in the front, that was supposed to be done with Nelson studs under a beam. Okay? And we called them up and said, in 10 years, when it starts getting corrosion around these, what happens to that thing? So we changed it. Okay? Your input matters. Every time you fix something, you learn from it, and the engineer learns, next time I'm going to design it different. But how it goes, the amount of weight that's required for some of these, when we talked about the threaded bolts, he says to me there's 175,000 pounds on that. I want a 12-inch bolt. I want it to go deep into the pile cap. That's his call. Okay?
To back up on that, when Joe's talking about 980, and obviously we have to cut that out because we can't use addresses. Even if the engineer had come back and said, no, this is how we want it, this is how it's going to be, this is how I want you to do it, that's fine. But that information is all done in email. It's all kept. In fact, a document like that belongs going to their PAs and being stored somewhere where if they ever go back to it, we have it, it's available. Whether that's 5 or 10 years from now, we can deal with it. I've been in depositions that were 10 years after we built the house for things that happened 10 years later. Documentation is huge, whether you're in the shell or whether you're in finishes. Doesn't matter.
Okay.
Well, what is the impact on the blowout on the process?
Just wanted to say blowout.
Blowouts are nasty, okay? Because what winds up happening is it never blows out at the bottom. It always blows out by the time you get enough weight up that, now it's pushing down. The more concrete, the more you push down. What winds up happening usually is you get a whole herd of people there with shovels, getting it out, trying to put it somewhere it's usable, and rebracing this wall, okay? It happens, okay? It shouldn't, but it does. 1640? You could take it out. When we did a residence, okay, there was a different kind of floor structure that was specified. We poured half the structure and it fell in. because it was, I forgot the name of that system. What was it? I can't use it anymore. I don't want to say it. Okay, so we called the engineer. We said, we're going to frame this traditionally. We're going to get through it. So we braced it up. We put shoring underneath it. We, on site, immediately framed rebar cages in the thing. We did the whole thing. Sent the engineer pictures. He approved it. We poured the slab. Okay? That's not something anybody did wrong here. That was a bad design. We did a job just about a couple of years ago where the morning of the pour, we had like 12 trucks coming to pour pile caps. We had to put these embeds for columns into the pile caps, and they called me at 6:30 in the morning and said, you know what, I think I was off by 3 inches. And we had to get a herd of people out there to relocate all of these pile caps and move them 3 inches before the concrete trucks got there. Okay? It happens. Okay? You do your best to avoid it, but how you deal with it is what makes us professional. Okay?
The cavity caps, they're simple, but they're very necessary. If you have a house like I'm building, it's a small spread footer. A cavity cap is going to dictate the weight that's actually on that footer. So if they're not in and they're poured,
That's a good point.
stress the footer.
Everything we build is based on a weight. The engineer determines how much weight is coming down a column, how much weight is coming down a grade beam. He'll change the grade beam dimension based on the amount of weight that's coming down. He calculates how much weight is in there by filled cells. If you fill cells that aren't supposed to be filled, the weight increases. Good point. Anybody else?
I just want to say one thing, guys. All of these things that we see and these terms that we're learning, probably the most important thing is to realize that just because the guys on the job are doing it doesn't mean that it's correct. It's our job to make sure that the spacing on the hoops are correct, the size of the hoops are correct. And by that, is it a number 3 hoop? Is it a number 4 hoop? Is it an 8-inch spacing or is it a 12-inch spacing? The distance between the embed plates. We have to verify all of those things. I can assure you that they do it wrong a lot. So you have to look at the plans, you have to verify all of that information. That's a critical part, not only just learning what these things are, but actually double checking and verifying that what's on the plans is actually what's being put into the field.
And guys, when you're in the field, if you get into a situation like this and you've been asked to go check these things and you don't know, we don't have a team of people that are going to just call you stupid and tell you to go away and figure it out. We have a team of people that want you to learn, that want you to understand, that want you to be able to look at the plans, understand the plans, and then go out and double check for what Marion and Joe are saying. That's the type of business we run. So if you don't ask a question and then you screw up, that's when you're going to have hell to pay.
I'd really recommend that if you're in town and if you have the chance, when there's a job like this going on, you come over and you walk it. After work, during lunch, see this all. If you've never seen it, or if you've never seen it to this extent, walk through. Make sure you understand everything that you're looking at. If you don't ask a question, there's a whole group of people here who can answer your questions. People call me up, and I'm so glad they do after these classes to say, you know, how does this happen? Or what do I do in this location? That's great. That means people are paying attention to things. Okay? Don't be afraid to ask. Marion's here, I'm here, you know, Carl's here, and supers are here. Ask the questions. Okay? Everybody good? Okay?
Thank you, Joe.
You're good. Thanks, guys.